I want to tell you, as you join the faculty, FAME has started a program. The name, we call it FAME Pro, is for people who are starting in their careers, and we invite them to send a research idea. And if they don't have a research mentor, we identify a research mentor, and Amy is very critical in this program in helping us really get biostatisticians involved early in the whole project. And we're finding, and the CTSA actually gives those people that we select vouchers to get projects or get certain core resources such as biostatistical support. So if you come on and you continue and join in the faculty, this is a program we'd really encourage you to think about applying for. So as I mentioned in one of the slides, I'd like to make this a little practical at this time and give you 5 or 10 minutes to sit down and try to, at your seat, write a good research question. And obviously, you probably in 10 minutes won't, come up with the best research question, but maybe this is something that you're already working on and you're thinking about working, and try to use some of the elements that we've just talked about here over the last 20, 25 minutes or so, or 35, 40 minutes, and see if you can compose a good research question. And then I won't try to put you on the spot, but we'll go around and see what kinds of things that you come up with, and we can share them and see, what kinds of things you think of and how we might improve them or where they're good. So let's take about 10 minutes to do that. So. Does everybody have something to write on and So we're recording this, so I need to stand up here instead of walking around. So how are you doing with, anybody want to volunteer a research question that they've written? You look like you've been working on it really hard, so what, and we won't make fun of you or anything, or, so what, and I'm going to repeat that in the microphone so the recording can be, but what did you come up with?
So one question I've had for a while is why do some patients with metastatic cancer have complete or whole responses to immunotherapy while others have no response?
What a crazy question. No, that's a good question. No, I like that. So just to repeat for the, make sure I got it right. Why do some patients with, was it specifically metastatic cancer, have a good response to immunotherapy and some don't? Yeah. Good. What do you all think about that? Any critiques, comments, anything? I mean, I think that's, to me, that's a good start because we think about some of the things that's obviously, it's certainly a very important and useful question. As far as I know, I'm a cardiologist, but as far as I know, we haven't figured that answer out yet. And, you might, eventually, refine that to more specific cancers, that, like melanomas or things that are known to have a strong immunobasis. But I think, you've got a good framework for a good start on a good research question. Anybody else? You're sitting in the front row. You're going to get called on. So.
I think it's a good start, but maybe it's too big, too broad.
Mm-hmm.
Maybe,
Mm-hmm.
I don't know, maybe you should be thinking in what kind of age patients or
Right.
maybe more
Right.
specific.
Good, but I was actually asking about your own research question.
I'm sorry.
So now he can critique yours too. Okay. No, it's great. Yeah.
So I do veterinary clinical microbiology.
Mm-hmm.
And then sometimes not frequently, we need to do salmonella surveillance in our hospital.
Mm-hmm.
And recently, it has been a push to have faster results.
Mm-hmm.
So the question that I was asking myself is, which is the best and faster methods to test salmonella when we are doing salmonella surveillance?
Okay.
In
So.
the environment of the hospital,
Right.
veterinary hospital.
So the question is, are the more rapid techniques as reliable, perhaps, as, okay, good. Yeah, that brings back memories, because my daughter, who I mentioned, got her PhD when she was getting her MPH in veterinary public health, was studying, I think it was salmonella in geese. So she got to run around and collect goose guano and all over the place, and that was an interesting experience for her. So, but yeah, so okay, good. One more before, yeah.
Okay. What factors predict bowel perforation and refractory diffuse large B-cell lymphoma treated with CAR T-cell therapy?
Oh, okay. So what's great? That sounds to me very, specific. It's got a very, specific focus. It's, a very defined group of patients, a very specific question, and sort of like the question I asked, what are factors might lend itself to a variety of factors to be tested maybe in some kind of model or something. So great, yeah. And so I thought you were going to say, what are the factors that predict coronary artery disease and transplant pay. No, that's another story. It's a project we're working on. So, okay, good. So I think some good examples, good, starting points. So obviously, as you continue, further refining your questions, and then very importantly, as I said, the next step is to get a great biostatistical colleague, just as you're about to hear from. So to tell you, what are some of the next stages. So thanks for listening and good luck with your projects, and hopefully we'll see you around. So. Oh, yeah, maybe take 5, maybe you want to do that? Definitely stretch if you
Get some caffeine.
Lunch coffee? How's it going? Have you had anything?
Well, thanks again. Okay, thanks. We'll see you all later. Yeah, that's right. Yeah, it's actually getting some things that, you can get diverted from that you miss. So, so it's nice.
I think on that public radio show, the quiz show they broadcast on Saturdays.
Oh, NPR?
Yeah, NPR.
Oh, what's that? Wait, don't, is it,
No,
wait, don't tell me.
No, it's the one that comes after it. It's
Oh.
from
Goodness.
from Brooklyn. They mentioned they have a 32-sided die or
Oh,
something. I'm not
goodness.
sure if there's actually that.
That would be
It's
pretty
a huge
interesting.
number, and I wonder, actually, are they just being sarcastic, or is it really that many sizes?
I would, you know what, I would not be
You know,
surprised if there is an
They're
actual,
just trying to get the order by 2 or 3 people. Yeah, much bigger dice.
all braced ourselves? Are we ready to talk about statistics now?
Oh my God.
Okay. All right, it's always, I feel like I hate being at this podium too. You know, this is always a tough spot because first of all, I'm following Dr. Binkley and he's just such a great speaker, so that kind of sets the bar high. You've already been sitting here for an hour very patiently, so personally I know my attention would be flagging, and we're talking about statistics, so this is like triple whammy. So I just want to say up front that how much I just really appreciate you coming here. I appreciate your time. I appreciate your attention. I'm hoping today this talk will be maybe not super interesting, but I hope it will be useful. I'm going to do my best, okay, but this is what we're working with here. So my name is Amy Lehman. I'm a master's level statistician, so I love it when he gave me a promotion, but I'm not Dr. Lehman. I'm just Amy Lehman. I work at the Center for Biostatistics in the Department of Biomedical Informatics. In January, this has been 18 years I've been here at the university working, so it just, time does fly, so yes, I'm feeling kind of like a dinosaur when I say that. And so today we're going to talk about sample size and statistical power. Now, Dr. Binkley in the last talk said that your research question should be simple enough that you can explain to a 6-year-old, and I was kind of, when he said that, I was kind of laughing because I have 2 kids. My son is 11 and my daughter is 8, and when I was working on this presentation at home, they were like, "What are you doing?" And so I said, "Let me explain to you," and I made it 30 seconds into the talk and they just took off. So I failed to explain this to an 11-year-old and an 8-year-old. I think 6 would be worse, so just to warn you here. Now, let's talk about what we're going to do after we come up with our great research questions. So Dr. Binkley gave you a lot of tips about how to come up with a research question that's interesting, that's novel. So now you have that. Usually the next question you're asking is, number one question that I get as a statistician is, well, okay, how many do I need? How many patients do I need? How many charts do I need to review? For those of you doing basic science, I don't know if anyone here does basic science, how many mice do I need? How many cell line replicates do I need to do? And so we're going to talk about that a little bit today. Now, because it's small, I kind of want to ask you guys, what is your statistical background? Have you guys, most of you probably have had some training in statistics or, been forced to sit through some statistics courses. Have any of you ever done sample size calculations or used online? Right. So I'm going to say up front that technology is amazing these days. There are so many different online calculators and available resources to actually do sample size calculations, kind of very easily. So the point of this talk is not going to be to pull up one of those online calculators and actually go through each one, let's put in 30 here and 20 here. But instead, I want to give you kind of an overview, kind of step back and tell you about some of the principles behind that. So for those of you who have had this before, this might be a refresher, but kind of explain a little bit about what those numbers mean. So when you're talking about power and alpha and you're kind of putting these numbers in, what are the assumptions you're making, to make sure that your sample size makes sense. So it's going to be stepping back a little bit. I'm going to give you some examples. Hopefully this will be useful, but we're not going to actually go through an actual calculator and put stuff in, just so we know that. And one more thing I just want to kind of give a disclaimer, and I do this for all my stats talks, is that in the time we have together, which is roughly an hour, which may seem like an eternity on your end, and on my end it's very short, I'm not going to be able to give you all the information that you need to kind of go off on your careers and go off and do perfect sample size calculations. I wish, even though there are so many great resources, you've probably seen a lot of those. YouTube, which I consider the font of all knowledge, has lots of stats resources. But that's really not complete. So if there were a book or a quick reference that I could give to you that an hour that would give you everything you need to know, I would do that, but it does not exist. And I will say this, that if this product does exist, it would probably be as reliable as this product right here. So in other words, not too reliable. Now, for those of you that were not even slightly amused by that, I'm going to warn you that the humor only is going to go down from here. It's funny because everyone has their own sense of humor, and so I'm thinking haha, I'm so funny. And then about a month ago, I was in another talk, and they kept on pointing these little jokes up, and I was thinking, boy, I don't really think those are funny. Ugh, did I change my talk? No. So anyway, but I'm just going to warn you, if you thought this was not funny, this is about the level we're going to be staying at for the rest of the talk. Okay. moving on. So before we talk about what is sample size, what is a power calculation, we need, unfortunately, to kind of do some background just to kind of make sure that we're all on the same page before we get to the good stuff. So I'm going to talk about the scientific framework. So, you know, when we kind of talk about power or sample size, how are we kind of framing our question? So there's going to be a little bit of formulas and notation, very, very little. I try to avoid formulas like the plague when I give talks, just because I know your eyes start glazing over. There'll be just a little bit of that, just so when you see this in the future that you will be, you know, you'll kind of remind yourself of what that is. I'm also going to spend some time talking about p-values. All of you have here, it sounds like you've all at least heard about a p-value or know what that is, or you know, if I call on you, you wouldn't define it necessarily, but you've seen it. P-values are so important to our research that I want to spend a little time talking about that before we get into the actual power, because they're all related. Okay, so that's just kind of give you kind of a map of where we're going. I'm going to try to break this up so it won't be so boring. So there'll be some surprises as we move on in the talk here. And you should be very worried right now. Okay, so let's review the typical scientific framework. So anytime you've taken an intro stats class, you might have talked about hypothesis testing. Dr. Binkley kind of very briefly threw up like that null and alternative hypothesis. How many of you, before we start, have seen, at least heard about null alternative hypothesis in some kind of stats course? Or is that something totally foreign to you? I'm assuming most of you have seen that. So we're just going to kind of review here. So you take your kind of vague, not vague, but very broad research question, and usually when you're actually talking about doing an experiment, you frame it in terms of two competing hypotheses. Okay, so recall the null hypothesis, which a lot of times we denote as H naught, is really what we consider the status quo. It's what we're going to assume to be true unless we have strong evidence to suggest otherwise. In many cases, we call this, usually a lot of times, this can be considered like a no difference. Not always, but typically in a lot of experiments, the null is a no difference kind of thing. The alternative hypothesis, which is something that we want to prove. So in other words, this is why we're running the experiment. Typically, in this case, we would consider that to be a difference. So I'll go through a concrete example. But the idea is that you have these two competing hypotheses, you collect data, and then see if does your data fit, which hypothesis does your data fit better, okay? Now one thing, and again, Dr. Binkley briefly mentioned this, and this might be considered a little bit of a nuance, but I do think it's important, is that when you run an experiment, we either reject the null hypothesis in favor of the alternative, or we fail to reject. We never do what we call accept the null hypothesis. And when you're taught this in statistics courses, you might be told it's kind of similar to like the criminal justice system, where legally you either convict someone or you fail to convict. You never prove someone is innocent. You just fail to prove that they're guilty. The same thing happens in science. Now, I know a lot of you might be thinking that's kind of a nuance, you know, kind of semantics. But I think this actually does come up a lot of times when you're interpreting your results. So if you say, for example, moving ahead, you run an experiment, get a large p-value, you have not proved, for example, that your two groups are equivalent or the same. And I see a lot of times that people interpret that the same. The groups are identical, p equals 0.2. No, you didn't really prove that they're identical, you just failed to show that they are different. So anyway, this is again, a lot of people might think it's a nuance, but I think it's still something important to keep in the back of your mind when you're kind of looking at these two hypotheses. All right, this is the slide where all of the notation is going to be. So once we get through this, we should be smooth sailing. When we are making decisions, as we are conducting experiments, we have to be careful about making mistakes. And we classify those mistakes into two camps. So let's talk about these. Type 1 versus type 2 errors. You've seen this before. So we're going to call alpha, usually we denote that as alpha, is what we call the type 1 error rate. And what do we mean by a type 1 error? We mean how often we find what's called a false positive. So when you conduct your experiment, you may conclude there is a difference. You may conclude the alternative hypothesis. You're hoping that's the truth, but you may make a mistake. We hope to minimize those mistakes, but we're going to denote how often that happens as alpha, the type 1 error rate. Okay? Conversely, we call beta the type 2 error rate. And it's the actual opposite. It's what we call a false negative. Okay? So in other words, we don't conclude that there's a strong difference, but really there was, okay? And again, I think it's kind of tough to give these kinds of definitions just in a row, so we'll kind of explain some more in the next slide. Hopefully this will kind of jog some memories. And so then if beta is the type 2 error rate, then 1 minus beta is what we call power. So how often we can detect a true difference. So when we're designing our experiments and when we're coming up with power and sample size, we actually want to minimize these errors and we want to maximize our power. That's what we really want to do when I say a sample size. I want to make sure that when I'm conducting my experiment, I have high power, so basically I can detect differences that I want, and I'm not going to be making a lot of false positives. Okay? Again, these definitions are very dry in textbooks, so I'm just going to give a little example just to make sure that we can maybe understand what we're talking about here. So here's an example. Suppose you are investigating whether a certain brand new weight loss drug, I'm going to call it drug X, actually works. Okay, so this is your researcher and you're like, I'm looking into drug X. Okay, if it works, I'm going to go on Shark Tank. I'm going to market this. I'm going to become rich. Okay, so I'm going to design an experiment. So what am I going to do? Work out some of the details, but you're going to get a couple groups of people. You're going to give one group of people drug X, right? One group of people, placebo, and let's follow them for 7 days because this is a 7-day weight loss pill, okay? All right, so now, and because you're a diligent researcher, you make sure the groups are all equal, they're all about the same weight, blah, blah, blah. Okay. Again, formulating your research question in terms of hypotheses, the null hypothesis, what you're going to assume to be true unless you have strong evidence to reject, is that drug X is no different from a placebo. So if I measured the weight loss between the two groups, I'm not going to see a big difference. What you'd like to see is the alternative hypothesis. You would like to see that the patients given drug X are going to lose a bunch more weight than the placebo, okay? That there's going to be a difference, okay? So does everyone understand the two hypotheses that we constructed here from our drug X? Okay, so we run the experiment. You collect all your patients, you give them the drugs, you kind of have a weigh-in at the beginning and the end. All right. Let's talk about what we conclude and if that's going to be true or not. So let's start over here. All right, so if you look at this first little row here, this is what happens in the experiment. So suppose we ran the experiment, we took the two groups and we found that, my drug X group lost about the same amount of weight as the placebo group. So I'm going to conclude that my drug didn't work. Okay, drug X is really not working. Now, we don't know what the truth is, but suppose that the truth is the drug X didn't work, you made a correct decision. Okay, your experiment kind of concludes with the truth. However, suppose drug X is really amazing and just somehow there was some kind of experimental weirdness and you didn't find that difference. Well, you then just made a false negative. Your experiment did not conclude that drug X worked, but it really did. Okay? Unfortunately, you don't know what the truth is, but these are the possible decisions that can be made. The other thing you could maybe conclude from this is suppose you ran this experiment and you found that drug X patients lost an average of 30 pounds more than placebo. And you're like, wow, drug X really works, okay? Well, if drug X really didn't work, if there was some kind of shenanigans going on or who knows, some kind of weird things, you just made a false positive. You're concluding that the drug X is amazing and works when it didn't work at all. That's a mistake. And of course, if drug X really works, then your experiment made the correct decision, okay? So does everyone understand the correspondence between experimental results and what the unknown truth is? Okay? So this false positive down here, for example, concluding that drug X works when it really doesn't, is what we call a false positive. We call that a type 1 error, and that's what we want to minimize in our experiments, okay? It's like and again, with the criminal justice system analogy, that's like saying someone's guilty when they're not guilty. Okay, usually that's considered a pretty big thing. Concluding that, for example, that drug X works when it really does work, that was the correct decision. That's power. That's what we want to maximize, right? We want to find when the drug really works. We want to be able to find that it works. We want to design our experiment. Okay. And so, as you can see here, I'm kind of filling in here all of the alphas and betas according to this matrix here. So the false positive, the type 1 error rate is alpha, okay? The power is what we called 1 minus beta. This false negative where we saw that, drug X really worked, but for some reason our experiment it didn't. That's the false negative beta. And then again, 1 minus alpha is the correct decision. Now typically, and you probably have seen this in experiments, typically we set alpha to be 0.05, right? 5% type 1 error rate. Power, usually when you see power in literature, 80 to 90%. We'll go into that a little more later, but just so you can kind of get an idea what some kind of numbers we're talking about. So in other words, typically when we're setting this up, we're setting it up so that the type 1 error, the amount of times that we would make a false positive is around 5%. Our power, our ability to detect a difference when really it is, 80 to 90%. Okay? And so usually when we talk about sample size, we're talking in terms of these kinds of parameters. Any questions about that? Does this kind of bring back some really good memories of all those fun times in stats class? Enjoying that, right? All right. Okay, so scientific framework. So the reason why we wanted to go into that scientific framework is a lot of times in your sample size, or it should be, in your sample size calculators, they're going to ask you for power or beta. They will ask you for alpha, or the type 1 error rate. That affects the sample size. Okay, so that's just so you know it goes into it. All right. Before we go into the nuts and bolts of power and sample size, I want to spend a little bit of time talking about p-values. Okay, p-values are so important in research today, whether we like it or not. Okay, and whether you've done research with p-values or not. I mean, p-values are right now sort of like the currency by which we kind of do research. You know that when you're submitting a manuscript or making a claim, most likely they're going to expect to see a p-value backing that up. So let's recall what that is. So the definition of that is that the p-value is the probability of obtaining the sample result or something even more extreme if the null hypothesis is true. Does that definition ring any bells, or you've seen something like that before? In other words, the question is asking, what is the probability that we found this result by chance? Okay. So for example, if drug X really didn't work, and was about the same as placebo, what's the chance that those patients would just lose, on average, 30 pounds more? Okay. Pretty unlikely. Makes us think that the hypothesis that the drug X didn't work might not be true. All right. P-values, now, fortunately for you, we don't have time to go fully into the history of the p-value, which I've done in other talks. But just to give you just a really brief background, p-values were, the concept of the p-value was first described by this famous British mathematician, geneticist named Ronald Fisher. So if you've heard of something like Fisher's exact test, this is Ronald Fisher. He's kind of known as the father of modern genetics. And he was the one who first described the idea of a p-value as a sliding scale of evidence to describe the disparity between what we observe and the null hypothesis. So the wider the disparity between our results and that null hypothesis, the smaller the p-value, the greater the evidence we have against the null hypothesis. So this is how he kind of envisioned the p-value, a tool for researchers to use to evaluate a claim. So small p-values suggest that the results are unlikely if the null hypothesis is true, makes us want to reject the null hypothesis in favor of the alternative. Now, interestingly enough, Fisher did not really ever say there's a critical value at which point you would magically decide yes or no. There was quite an interesting history behind that. But today, we typically, if the p-value is less than 5%, we will reject the null. Okay, that's pretty much convention. Probably pretty much everyone knows that. The goal of your research is to get a p less than 0.05, right? That's really what you want. Okay. Does everyone understand? Does everyone kind of have a vague idea now about, just refresh about p-values, what p-values are? Okay. All right. So again, just to review what we've talked about so far, we've talked about the scientific framework. We've talked about formulating two hypotheses, competing hypotheses, using a p-value to kind of make a decision about that. And again, no one's laughing. This is the kind of T-shirt that The funny thing is, even if you understand it, you're probably just like, yeah, But I think it's amazing. I'm seriously gonna go and try to buy this and wear it just to one of these talks, just to make it even more obnoxious. So. All right. So everyone understands kind of the steps that we do. We have these two competing hypotheses, we do some kind of appropriate statistical test, we get a p-value, we make a decision. Okay. So what's the issue? Well, the issue is that p-values, unfortunately, are misused and misinterpreted in research. Okay. So, first of all, that choice of 5% for significance, we design most of our studies for 5% significance. I'm not really sure where that number came from. So when I first started training as a statistician, I assumed that there was some kind of theoretical reasoning why 5% made a lot of sense. But there really isn't. If you kind of go back to the history, when Ronald Fisher was writing his book Design of Experiments in the early, it was like turn of the century, 1900s, they were publishing it. He thought it'd be nice to have some tables of results. And the publisher said, because there was limited space and publishing was expensive, could you suggest some cut points for significance? And he said, well, 5% sounds good. That's pretty reasonable. It literally was something as arbitrary as that. But for some reason, over the years, it's gotten kind of mutated with other schools of thought, and now people are so fixated on getting that p-value less than 0.05 or greater than 0.05. And because of that, there's an over-reliance today on p-values to make decisions in experiments. Okay, so we're kind of doing a little tangent here, but this is all kind of related to sample size power and designing your experiments. One of the biggest issues one of the main issues that we have is something called harking. Has anyone heard that term harking before? Harking stands for hypothesis after results known. So especially when you're doing some kind of exploratory data analysis, you're testing 50 different things. You look at the ones where the p-values are small, and then you kind of come up with some kind of biological reason why that had to be true. So letting the data completely drive your results, and then trying to construct a story around that. Okay. That path might get you into trouble later on. I'm not saying that, I'm not saying that there isn't a role for exploratory analyses, but the problem is when people do multiple tests like that, screen thousands and thousands or hundreds and hundreds of factors, fixate on the one, and then pretend like that's what they were looking at all along. So that's a problem. The other thing I have a problem with is when you use a 5% cut point, it's really a very cut and dry kind of thing. So if your p-value is 0.049, you're going to say, drug X works, let's go to Shark Tank. If p is 0.051, you're like, well, shoot, what am I going to do? I can't do anything about that. Which really, when we think about it, the p-value is just a probability. When Ronald Fisher developed it, a p-value is literally a probability. So if I told you you had a 4.9% chance of being hit by lightning, and you had a 5.1% chance of being hit by lightning, okay, you probably would be feeling you're about in the same boat. But in science, for some reason, we treat those as two totally different things, okay? And so one thing to keep in mind, and this is why I'm talking about this, is p-values are functions of sample size. Okay? So if your sample size is very large, you have quite high power or ability to get very, very small p-values, and vice versa. If you're only using n of 3, it's really difficult to get a really tiny p-value. And that's one of the reasons why we talk about sample size later on, because of p-values. But just keep that in mind when you get to that analysis point of your study. One of the things that we're going to talk about that's needed when you're kind of determining sample size is being able to differentiate between clinical versus statistical significance. So one thing I'm going to really strongly encourage you as you move forward in research is to not just look at the p-value to determine the significance of your study. So let me show you an example. This was pretty old. It's a 1998 Reuters news article about a study that was published in Nature showing that men born in the spring were taller. Okay, it was published in Nature, so this is kind of a big deal. Okay, and it made all the news outlets. And it sounds kind of interesting. So men born in the spring are taller? Until you read the article and realize that the height advantage was 0.6 centimeters. Okay, I've said this many times. When I've talked about this example, I'm not a doctor, I'm not a clinician, but to me that doesn't sound very clinically interesting. Okay, 0.6 centimeters. Probably not that significant. But it had a very small p-value when you compared spring versus other months. Why? Because if you look at the first article, they had over 500,000 men in their study. So the huge sample size translated to a tiny, tiny p-value. Whether or not that result's clinically interesting, not really. I suspect not, because there hasn't been a lot of follow-up on this startling result. So keep in mind the difference between statistical versus clinical significance. Okay. Last thing, and this definitely applies to when you design your study, is multiple comparisons. So your research question or hypothesis or area of research may not be just one simple question. You might have multiple questions. You know, it might not be a simple, you know, drug X works yes or no. You might be exploring multiple factors, you know, testing multiple groups or multiple outcomes, okay? What concerns me is, the problem is, when you do multiple comparisons, you always have to keep in the back of the mind the concern about phishing or for significance, or what we call p-hacking, okay? And so what I mean is taking multiple groups, testing them, taking multiple outcomes, multiple predictive factors, and testing them over and over at the 0.05 level, and then taking those out that have p less than 0.05 without taking into account the fact that the more tests you run, the more likely you are to get a false positive. What's really interesting is that there was a JAMA review article in 2016 that reviewed all, I believe it was all articles published in PubMed, as well as abstracts from 1990 to 2015. So they had a p-value in them. I believe there were over 12 million published articles in this time period, and over 800,000 abstracts or something like that. I mean, it's not surprising when we look at the volume of literature. And almost every single one of them reported at least one p-value of 0.05 or lower. So basically, we're finding significance everywhere, right? Everything is significant. Does that translate to legitimate discoveries? Well, if we had 12 million articles, I mean, if everything was technically clinically significant, we'd be just like overflowing with significant results to follow up on, but that's not necessarily true. So we are all fixated when we do research on getting that p less than 0.05, and if we don't get that, we kind of want to kind of feel how to fix that. But clearly something is going on here, okay? And what I suspect is going on is one of the things is for false positives. So if you do, so for example, you run a study, your main comparison is not significant. What's your first reaction maybe? You know, you don't want to trash that study, you've done a lot of work. You might say, well, is there a specific subgroup where this might work better? Or what if I look at these other factors? Or what if I kind of play with it a little bit until I get a significant result, and then I want to report that, contributing to the 96% positive results, okay? What I'm going to tell you is I think that's actually a very dangerous practice to do, okay? And because you guys have been so good, and you've been so patient, and you've been listening to this very kind of dry talk, we're going to break it up now, and we're going to play a game, okay? A statistics game. How could that go wrong? All right, so it's game time. For this game, I'm going to need 2 contestants, okay? Now, this is not going to be having you talk to me about your research project. So I'm going to tell you up front. All you have to do is push a button, okay? I'm not going to ask you any hard questions, and I have prizes. So, given that, do I have 2 volunteers to help me play this game? I got prizes. Yes, one. I need one more break. There you go. You got it. All right. Okay, hang on. Because this is a super high-tech... Wait. You can't come up yet. Hang on. You can't come up yet. All right. Now you can come up. Let's see if I can get this to work. My high-tech... Oh, that's not it. Come on to this one. Okay, come on up now. Yes, you can come up. All right, everyone give them a round of applause. Yay. Okay. Thank you for being my very brave concierge. Who would like to be the first? You were the first volunteer, okay. So you get the first choice. All right. I'm sorry, what was your name again?
I'm Andrew.
Andrew, nice. I'm so happy you came up here. All right, what we're going to do is we're going to play a dice game, okay? Now, actually, I have a physical die here that you could actually roll, but because it's hard for people to see, we're gonna do it online and roll it virtually so you can all see the results. So instead of rolling, if you really want to roll it, you can.
I'll press the button.
So this is what we're gonna do. This is the game we're gonna play. I want you to roll a die, a single die. You win as long as you don't roll a 6. Anything but a 6, and you win one of my amazing prizes. Okay? So everyone understand the rules of the game? All you have to do now is.
Should I?
You can do it.
Okay.
All right, everyone. You rolled a 4, so hang on. Okay, everyone give him a round of applause. Thank you very much. All right, so you won my amazing game. So you get to pick one of those.
Okay.
All right, so that was it. Easy, right? So thank you very much.
Thanks.
Thank you, Andrew. All right. Pretty good game, huh? All you do is push a button. All right, now.
I'm also Andrew.
Andrew number 2. All right, Andrew. We're gonna play a similar game, but it's a little different. So instead of rolling 1 die, you need to roll 10 dice. And if you roll a 6 on any one of those, you lose. If not, you win. Okay? So is that clear? Okay, now, because a couple times we've done this, and now you have a choice. You can push this button 10 times, okay? But just make sure that you pause long enough so we can read it. Or if you agree with the whole idea of randomness, you can just roll 10 at once, 10 separate dice at once. It doesn't make a difference to me. I thought you'd like, do you want to press it 10 times, or would you rather just do it once?
You can do it once.
Just do it once? You're like, get me off this stage as fast. So we're going to assume, because this is computer generated, the dice are truly fair and random. So if we roll 10 separate dice, it's the same as rolling 1 10 times. Okay? All right. So you ready?
Yes.
So I got all set for you. So let's root for Andrew number 2. Let's see what happened.
Oh,
Oh my goodness!
Two
And so
sixes.
you got 2 6s. So I am so
that's
sorry.
slightly above probability.
Oh, we never. Hang on. So wait, I have.
You were like,
I am so sorry. But you know what? You've been such a good sport that I'll give you that anyway. So, all right, well, so thank you for Mr. Andrew number 2. All right. Okay, so these were the 2 games. So we just played 2 dice games. One where we rolled a die 1 time, one where we rolled a die 10 times. Here's my question for you. Which game is easier to win? And it's actually worked out. I played this before where like the first person rolls a 6 and you're just like, ugh. Which game if you had to play this game for something, which game would you rather play, the first one or the second? The first one. Okay, and the question is why? It's the same die. The probability of rolling a 6 is the same for both games. Why is game 1 therefore easier to win than game 2? Because I think you instinctively can kind of know that, when you roll a die once, the probability is 1 out of 6. But if you keep on doing that, eventually, right, that probability is not going to stay 1/6, it's going to go up to 1, correct? If we keep on rolling it long enough. And if you actually work out the math, the probability of rolling a 6 in one roll is 17%, 1 out of 6. But if you actually work it out, these independent events, the probability of rolling a 6 at least 10 rolls is 84%. So I kind of did stack the game against you, but I appreciate you being a good sport. So why am I talking about this? Because this dice game is sort of an illustration of what happens with type 1 error when we do multiple tests, okay? So typically we set the type 1 error rate to be 5%, which means it's almost like rolling a die. That means we accept that 5% of the time that we will falsely reject, okay, when we should not reject. We accept that 5% is a low enough, probability that's okay. But the more tests we run, okay, that probability, that type 1 error rate does not stay at 5%. So if you do 10 tests at 5%, your overall type 1 error rate is not 5%. It actually goes up to 40%. Okay? 50 tests goes up to almost 100%. So especially today with like genetics, multiple factors, data digging, type 1 error is something that we really worry about. Okay? So I want you to keep this in mind as you're designing your experiments, that if you're using 5% and you have multiple tests or outcomes, you might want to adjust that. Otherwise, your type 1 error rate is not going to actually be 5%. It's going to be something much higher. Okay? Did that example help at all? Or if not, at least, it's something a little different to do. Okay, and for those of you who think that maybe this is me, a lot of times as a statistician, people are kind of like, you're just kind of nitpicking. I've done this before. The world hasn't ended. Have you seen in the news last year, there was a very recent about Brian Wansink? I think that's how you pronounce his name. Have you heard about this? Okay, He was a very famous, he's a pretty famous Cornell researcher. He had his own food lab. He did all sorts of studies looking at psychology in food. So I didn't realize this, but for example, have you ever seen those 100-calorie little snack packs? That was based on his research. I know that Michelle Obama, some of her food recommendations for the kids were based on his research. He does a lot about psychology and research. Well, so he was well established, well funded, very successful. It turns out that he resigned last year, having had multiple papers retracted for bad statistical practices, among those p-hacking. Okay, it's a simplification to say that p-hacking caused the downfall of his career because there were multiple things, but that was one of the things he did. So the moral of the story is that it doesn't matter how successful or high up you are, everyone is vulnerable to kind of bad statistical practices, and this is something that's very, very insidious. Okay, so always listen to your statistician. Okay. All right, so there's been a lot of controversy about p-values, especially a few years ago when a psychology journal banned p-values from their publication, and in the stat world that created major waves. I'm sure the rest of you managed to sleep at night, but for statisticians it was a very exciting time. So the ASA, the American Statistical Association, actually took the unprecedented step of gathering together top statisticians and giving their recommendations for p-values. And I kind of want to share those with you. These are just general guidelines. So regardless of how you feel about p-values and should be used, if you use them, they should never be used alone to determine significance. So always keep in mind the difference between clinical versus statistical. If you get a statistically significant result, check the clinical meaning of that. Are these differences that I'm finding clinically meaningful? That might help you interpret your result. The other thing, and this is also part of what sank Dr. Wansingh's career, is you should always have full transparency in reporting, no cherry picking of results. If you screen 1,000 cytokines or genes and find one or two that are interesting, you should really probably report that you actually screened 1,000. You shouldn't pretend like this was the only gene that you were interested in. And avoid p-hacking by focusing your research. So one of the best ways you can do that is after you kind of develop your research question, to come talk with a statistician so we can kind of really get down to the nuts and bolts. And we're almost to the sample size part, but that's one of the things that we will work out too. Okay? So we spent quite a bit of time talking about p-values now. So now we're finally ready to actually get to the point of this talk about what is a power analysis. So we kind of had a little background on the scientific process and p-values. What is a power analysis? So the question is to answer that simple question, how many subjects, replicates, observations do I need to have a good chance of detecting the effect I'm looking for? Okay. Okay. And we'll go over this later. It should be said, this should be performed before you start running your experiments or collecting data. I have a slide later on talking about post hoc power. We'll go into that. But really, you should be doing this before you even start to even collect data, take your cell lines, gather those mice. And this is the thing that I think is kind of, sometimes if you've never really done a lot of this before, a lot of times that researchers think this is something that should be done, the next obvious question, but in my mind as a statistician, this is really something that happens almost at the end of the study, because the information that you need means that you need to have worked out almost all the details of your study to perform that. So the design details, for example, we'll go into. Okay, so one thing I should also mention, in your cases, in my experience, there are two times when we really need to worry about power calculations, or most times investigators need that. The first one is prior to performing an actual experiment. You're about to do something and you want to know how many I need to run. The second one is if you're proposing research for funding and you need it for a proposal. You need to have some kind of justification. All right, so we're going to talk about both cases, and I'm going to give you an example for that second one of what I consider a good and bad example of a sample size calculation. All right, what do we need to know? So before you actually go through that calculator, what do you need to know about your experiment to kind of successfully calculate sample size? There are kind of multiple categories. The first one is the design aspects of your study. So for example, what are your primary comparisons of interest and how are they measured? Okay. Okay, so you maybe want to look at obesity, education and obesity. Okay, that's a great research question. I'm going to ask you, how are you measuring education? Is it, is there some sort of standardized test? Is there kind of grades? What is that? Obesity, are we looking at simply BMI? Are we looking at what time points, et cetera? How many groups treatments arms are there? Okay, a lot of times your research may not be a simple two-group comparison. It might be something a lot more complicated. These things all need to be worked out. The answers to these questions will determine what kind of statistical analysis you do use. And that statistical analysis will be used in your sample size calculation. So this absolutely needs to be at least determined before we even start talking about sample size. Okay. The second one is maybe the most important ones. We need estimates of what I call effect size and variability. Okay, what is effect size? Basically what I'm saying is what kind of difference, and again, we're assuming your hypothesis is going to be a difference hypothesis. If it's not, we can talk about that too. But most standard studies, you're looking for a difference. What kind of difference is clinically relevant, attainable, anticipated? The smaller the difference that you're looking to find, usually the more sample you need. Okay? If you're looking for a super large difference, you might not need as many. The second one is super important, variability. Okay? What I mean by that is how uniform are your observations going to behave? Okay? So if you're doing, say, a cell line experiment where you expect everything to be very uniform, there's not a lot of variability, you might not be a lot. If you're doing research on patients, humans are so variable, cancer, looking at primary cells or things like that, they react so differently. You may need more. So we need to have an estimate of how variable, how much we think those observations are going to vary before we actually calculate a sample size. Okay, any questions about that right now? Okay. The third category is the practical considerations. Okay. How many patients or subjects are available? You might be limited. In fact, everyone's limited. Probably no one here has the luxury of infinite time, infinite money, infinite resources. So we have constraints. So sometimes we have to work backwards, knowing what you have, what we can achieve. So for example, if you're studying a very, very rare disease and we know we can only get 10 patients in a 5-year span, we're probably not going to be able to answer that question about, involving a super involved randomized clinical trial where we do things like that. Attrition rates are another thing, especially in prospective studies, but also in retrospective studies too. You might have a lot of incomplete data in a retrospective data analysis. If you're doing a prospective study, patients drop out. If you're doing basic science and you're engrafting, for example, mice, you might not be able to engraft all the mice. You might have a failure rate. All those things need to be built in and buffered into the sample size. And the last thing we also need to do is set your type 1 error rate and your power. Usually those go in, as we call it, alpha and 1 minus beta. Now, typically, again, we set our alpha to 0.05, the caveat with the multiple comparisons. We will see that. And again, power is typically set to 80, 90%, but it may be different depending on the context of your study. Most of the times, as researchers, we think a false positive is a more serious error than a false negative. But if you're doing some sort of like cancer screening, a false negative might be worse than a false positive. So you might want to adjust that. But typically that's what we set those at. But it's very project specific. Okay, so these are the 4 basic categories of information, all that's needed to go into your sample size calculations. Okay, so basically what I'm saying is that there's a lot of work that goes up front after your research question before I can tell you how many subjects or patients that you need. Okay, now most of these you can kind of go on your own, but the one that usually trips up people is the idea of the effect size and variability. Right, because that usually requires some kind of external information that you may not have. You can decide on the design aspects, you might know about the practical information, alpha and beta, you can set yourself. But if you kind of have to get an idea of what kind of variability, where do you get that kind of information from? Or an effect size? What kind of differences would I expect to see? What does baseline look like? I have no idea. So where can I find this information? Here are some ideas for you guys if you are doing research and kind of need some preliminary information to kind of help inform sample size. One thing is basic numbers. Are you all familiar with the honest broker process here at OSU? I'm going to just pull up this website. Oh. That's interesting. I didn't know we had to do that. Let's see if I can get that on there. Okay. So sometimes when you're about to conduct a study, especially with patients or with medical records, you might not have any idea of how many patients are available. You know, I'm looking at males with a specific disease. I have no idea if I have hundreds of records I might be dealing with, thousands or not. So one thing is that you have the ability through this process right here to go to the Honest Broker data request and actually get some aggregate raw numbers before you actually submit your proposal. So if that helps you kind of get just a ballpark idea of what you need, you might be able to do that. So this is non-PHI, so this is only going to be summary or aggregate information, but sometimes those numbers are really helpful, especially if you're studying this disease and you want to know how many have a certain condition or meet certain basic criteria. You can use this to kind of get a basic ballpark estimate of what I'm dealing with. So do I know if at the outside I have 500 patients max, or do I only have 30 patients max? Okay, so that might be a resource that you have here, and we can send the link to that after the presentation.
Where does it pull? Is it just pulling off the EMR, like our
Yeah.
mapping chart? So it goes back to like, well, like 2011, 2009?
I'm not sure actually that's a good question. I'm not sure what the initial date, I don't know if Stuart, you have any idea what the beginning dates are on those?
I've heard it before, but
Yeah.
it may be something like it.
It might be something around two, yeah.
Is it kind of a rolling thing?
It does keep on updating, but I'm not sure what the minimum date on that is. It could be something like two, anyway. We have used this in the past for just to get us ballparks, estimates of just kind of idea of what numbers we're dealing with. Because sometimes if we're studying a condition that's so rare and specific, we'll know that we just don't have enough to even kind of proceed here. Another thing is if you've also done, sometimes other people have done retrospective chart reviews, and you can kind of use that information. Existing literature, I mean, all of you are going to do literature searches before you do this, before you do your research. And so if there are other studies that kind of have similar conditions, you can kind of use those. If you have the luxury of performing a pilot study to gather some preliminary numbers, that would also be a great thing. I know that this is not feasible for a lot of people, but if you have that luxury, getting at least some initial data is always helpful. So in the past, from my experience, most people use a combination of, say, existing literature to get this information, or they work with other people and they have some other kind of chart reviews. We also use this for basic numbers as well. Pilot studies are great, but sometimes not practical in a lot of those. But all these can be used to kind of get an idea of what kind of numbers we might be looking at. What's the expected mean of the control group? What kind of differences do I expect to see? You know, from the published literature, what kind of variability do I see? Okay. So I'm going to go through an example now, what I'm calling a quote-unquote straightforward example. I want to show you about some of the calculations and considerations that went into a sample size calculation that I performed, worked on. This is a randomized clinical trial that we worked on at the beginning of many years ago, at the beginning of my career. It was a prospective study called the Community Awareness and Resources and Education Initiative. It's called CARE. The goal was to address the high rates of cervical cancer in Ohio, Appalachia, which is the green counties located right there. So they recognized that the women in these counties had high rates of cervical cancer. They wanted to increase screening. So they decided on an intervention where they would train women in the community to act as lay health advisors, to kind of go and educate women, their peers, about the importance of getting screening. Okay, and they thought that having these lay health community contacts would help increase screening. This is versus, we want to look at screening rates versus usual care, which is we just mail the women a pamphlet about you should get screened for cervical cancer. The primary outcome was whether a woman received a Pap test within 12 months of randomization based on her medical record, so it's a simple yes-no. You know, was there a record of a Pap test within 12 months? So all the women coming in were in need of screening. And then we want to see if after getting the intervention, whether they got screened. The participants were female residents meeting eligibility criteria recruited from local clinics. Okay, so all of this is stuff that we worked out. So let's go through all these kind of aspects, the design aspects. So again, it's what I said. The primary outcome was the proportion of women who received a Pap test. We're comparing the proportions between the intervention control groups. So based on that, based on the nature of the outcome, it's a yes-no. We were looking at proportions. We were going to do a chi-square test. So again, that's factored into the sample size. We're also going to want to control for some factors. That also means logistic regression. We have a 0-1 outcome. All right. We also were going to do equal allocation to the intervention and control groups, so we knew that going in as well. Effect size variability. Now, in this case, we had the luxury of doing some pilot studies. So we kind of did some initial canvassing to get ideas, medical record reviews to get ideas of cervical cancer, of screening rates, and we knew that the average screening rate was about 40%. The investigators decided that a 20% increase in screening would be clinically meaningful. So what they wanted, that's the difference that they wanted, the minimum difference they wanted to detect. They were hoping this intervention would have a huge impact on screening rates. Okay, so we're looking for a 40 versus 60%. Some practical considerations, attrition was a huge factor because these are women in Ohio, Appalachia. Contacting was difficult, there are many challenges, so we anticipate about a 30% attrition rate. This is a huge randomized clinical trial. We had resources and budget to worry about. And also we wanted to make sure that we had enough numbers, not just to do that yes-no proportion, but also to do some kind of exploratory modeling as well. Again, we set our alpha at 0.05 and our power at 80%. So all this stuff was kind of worked out ahead of time. If you take those numbers and throw them into a calculator, we realized we needed 97 women per group to detect a 20% difference based on that test. We inflated that sample size to 140 for a 30% attrition rate. And so our final sample size that we gave them was we needed 280 women, 140 in each group, based on all of that information. Okay? Now, I say that that was a straightforward example, but that actually took almost a year of work, prep work, to kind of get to all those answers. Even though I call it straightforward, there was so much back and forth about that. We had to figure out our outcomes, what comparisons we wanted to do, treatment groups, time points, et cetera. Now, I know a lot of you don't have the luxury of doing that, but I think it's important to know that the time you spend now focusing your research is going to pay off in the end. And I want to show you, I hope this works, I want to show you a really quick clip from an old movie that I really love because I think it kind of talks about the idea of focusing your research unintentionally. This clip is from a 1995 movie, so real relevant and fresh. It's called Sabrina. I don't know if any of you have heard of the movie Sabrina. Occasionally someone will hear it and I'm like, wow. This is a 1995 movie. It's actually a remake of a more famous version with Humphrey Bogart and Audrey Hepburn. This version starred a younger Harrison Ford. It's not a very good movie, so I wouldn't recommend wasting your time. But there's a scene in here that I really love, that I think I've always stuck with me over the years. So I want to set up the scene for you. In this scene, a photographer is talking with their client about taking pictures and selecting shots to take. So keep your fingers crossed. Let's hope that this works.
Do you want a view from the house?
Sure.
Which one?
All of them.
More isn't always better, Lina. Sometimes it's just more. Pick one.
All right, so probably the setup was not even worth the payoff. But I love that idea of, again, just like in photography, more isn't always better. Sometimes it's just more. And I feel the same way happens in research. As you're kind of taking your concept and trying to come up with a sample size, you might be tempted to want to do everything with it. You want to test the 50 different factors and variables. You know, always keep in mind that more isn't always better. Sometimes it's just more. So I really recommend trying to focus your questions down and determine what is essential versus what is not essential when designing your study. Okay, so that was just a straightforward example of all the factors, all the information that we needed to do a sample size. Now, what about for those of you who are submitting for funding and need to write something about your sample size in your proposal? Okay, so I want to quickly give you an example of a write-up that I just recently came across as a reviewer, and I want to talk about some things in here. Okay, so here is a typical proposal. They had multiple aims. I'm not going to tell you more, a lot about it, but this is the statistical considerations for this aims. I know it's a lot of words. But I want to go through what their sample size power calculations are. So we have two aims, as you can see here. I'm going to highlight where they talk about sample size and power. So what they say here is we're going to do a bunch of tests. They'll be performed at least 3 times using two-sided t-tests with a 5% significance level. Okay, n equals 3, at least 3, so maybe more, we don't know. In this one, they say they're going to use 4 mice, and they claim it'll yield greater than 80% power for tumor volume comparisons, whatever those are. Okay. Again, as a reviewer, when I read this, it kind of made me a little unhappy because it's missing a lot of detail. Correct? There's a lot of detail. Tumor volume comparisons. It doesn't give any information about what we expect to find. What's the difference? There are multiple comparisons in here, and there's no mention of that. So I know that when you write proposals and you're talking about sample size, you kind of maybe want to gloss over that or just kind of put, you don't have a lot of space. But I'm going to say, as a reviewer, when I see this gives me a red flag because it makes me worry that you have not thought through your proposal thoroughly. And to me, this level of detail is not sufficient. Okay, so I'm going to give that a unhappy face. So if this is not sufficient, what would I consider an example of a good sample size? So here's another example. Again, this is a basic science example, but I want to show you the difference in these two. So in this one, it says here are the examples. We're going to measure 4 things. It says here 80% power check of 2-fold interaction effect, coefficient of variation of 30% based on a Vessier experience. Here's my alpha level, which is overall 0.05. But I knew I'm doing 4 comparisons, so I actually have adjusted the alpha level for each comparison to count for the multiple comparisons. We say which primary outcomes and 2 cell lines. Okay. So I just wanted to give you an example of the kind of details that we like to see, whether or not you understand all the details. But from this example, what kind of difference we're detecting. They want to look at a 2-fold difference. What kind of variability? So coefficient of variation is a measure of variability. We know our alpha level, and we know power in alpha, and it's been adjusted for multiple comparisons. Okay, so this is kind of an example of a write-up that has a lot more detail. So the goal for me as a statistician, when I see a statistical write-up, I would like to be able to have enough information that I can replicate that or verify the number. Okay, so I'm going to give this one a thumbs up. But also I'm going to give it an eye roll because you might guess I wrote this myself, so I'm just providing my own example. So yeah, it's kind of an eye roll as well. Okay. Any questions about this? I don't expect you to kind of fully understand all the details, but just to understand that when you write power calculations for proposals, the more detail, the better. The more detail provided shows the reviewer that you have thought through these experiments. When I see very vague statements about n equals 4 mice, it makes me worry that your project, you have not thought through all the details, and it might not be feasible. And that's actually some of the comments that I sent back to this first one. Okay? Any questions about that? And I know that there are constraints with, you don't have a lot of room, you're very compressed. I would try to squeeze as much detail in it as possible. A lot of times proposals do get dinged for lack of statistical detail. Okay, so again, this is not something we're expecting you to do on your own. We expect you to work on a statistician. So a few things to keep in mind. Many of you, again, have done sample size calculations, and you have these calculators, and you know that you can plug numbers in, and you can kind of, play around with the numbers and see what the effect of the size is. Okay. So if you're doing this, you might be tempted to play around with the parameters in order to achieve a desirable sample size. So you might throw some numbers in and get out 2 million, and you're like, oh, so I'm going to start, what happens if I increase my alpha? What if my power goes down? What if I do this and that? And then you play around with it till you get a number that looks good, and that's, yay, I'm good, okay? All of these things you can do. I just found this online, but there's tons of calculators. And so, for example, they ask you alpha, they want power, blah, blah, blah. Okay? I just want to warn you, if you're playing around with this, that if you start just mindlessly playing around this to get a smaller sample size, you might risk setting your study for failure. So all these parameters mean something, and they're meaningful. And I'm almost out of time, so I'm going to rush through this. So remember that CARE example we talked about? I want to show you, because it's a clinical trial with the luxury of seeing what happened. So I'm going to tell you what happened, because we've actually completed the study. Let me tell you, we said we needed 280, 140 per group to detect a 20% difference, 60 versus 40%. We completed the study. We actually got more than enough. We painstakingly got 145 in the intervention and 141 in the usual care group. Okay? When we actually analyzed the data, look at what happened. our control group proportions were spot on. So that pilot data really worked out. The actual baseline intervention rate was 42%, and we estimated 40%. But the intervention, we had powered it for a very large difference, and it was only a 9% difference, okay? So we failed to achieve statistical significance. So again, our assumptions matter in these sample size calculations. So again, the larger the difference, the smaller the sample size, but they actually kind of correspond to reality. So I am out of time, so I'm just going to, this is the last thing I just want to say really quickly, very, very quickly, is that you may have heard something called post hoc power. So you may have submitted something or gotten a non-significant result, and a reviewer comes back and says, can you do a power analysis to see what was the power you would have had with your study? The idea being that if you get a non-significant result, but you were highly powered, that maybe that might mean something. I just want to tell you that if you ever get that, come to talk to a statistician, because power calculations only should be done prospectively. This is a very nice article back here, but it makes absolutely no sense to do a post hoc power analysis. Power and p-values are inextricably linked. So if you have a large p-value, by definition you have low power. So the idea of doing a post hoc power calculation really doesn't make a lot of sense. So over the years, I've been asked several times to do post hoc power. We always will rebut that. So if you ever get a request for that, don't do it. Come to us and we can help you rebut that. Okay, so summary. Sample size calculations are performed before you start your study. They required a lot of detailed information, so you really need to work through all aspects of your study before you even begin to calculate this. So design aspects, effect size variability, practical considerations, and alpha in your power. And just please be careful when using statistical software to calculate sample size. And again, work with this. This is not a giant infomercial for working with a statistician, but again, as a statistician, we love working with you. These are complicated concepts, and we're happy to work with you. So. Yes, so anyway, I had a bunch more stuff, but ran out of time, so I just want to say thank you very much for your time.